first going to look at our integral test. There are a couple of key things that have to happen in order for us to use our integral test. So, one, again, remember it is lower on our list, so if I can use one of my other tests, I'm probably going to do that first, because as it kind of says, we're going to be taking an integral, which for some stuff can take longer. So that's why it's not necessarily high on our list. And then two, it has some specific requirements of our inside function. So the function must be continuous, it must be positive, and it must be decreasing. On the interval 1 to infinity. So if it's discontinuous at 0, that's okay, because we don't care. We just care about from 1 to infinity, because notice then that we are creating an integral, which is why it's called the integral test, because we're taking an integral from 1 to infinity of f of x, where f of x basically represents our sequence with x's instead of n's. And so then, like I said, it's pretty straightforward. If this integral is convergent, then the sum of our sequence will also be convergent. If the integral is divergent, then the sum of that sequence will also be divergent. So if we need our values, or sorry, if we need our a sub n to be decreasing, yes, but our x values are getting bigger and bigger and bigger and bigger, what do we think we're probably going to end up with a lot of? What type of thing? I actually looked at one a second ago. As something in it gets bigger, the whole thing gets smaller. A fraction, right? So I'm going to a lot of times have fractions in these cases, okay? Because as your variable gets bigger, if I have a fraction and my denominator is the one that's getting bigger, then the whole fraction is going to be decreasing. And since the decreasing is a requirement, we end up using this with a lot of fractions. Yes, no, maybe? Does that kind of make sense? Okay, let's look at some examples. Alright, so it says apply the integral test. It is nice on this one. It does say apply the integral test. Okay. But let's think about if I wanted to use one of my other ones. So going kind of like through our little flow chart that I gave you, okay. We don't know what a harmonic or a p-series is yet, but it's not one of those. Does that look like a geometric though? Is that just something to the n power? No. If I were to take the limit as n goes to infinity, what is that limit going to equal? 0. So can I use my nth term test? No, because it equals 0. Which is why then I have to do something else. So in this case, it's the integral test. So we're going to set up our integral. So again, I'm just going to treat it. So I have 1 to infinity of, I'm just going to replace my n's with x's. So we have an infinite integral here, so an improper integral. So what do I do with that? Cool. So I have the limit as b goes to infinity from 1 to b of my function. we're going to treat it as two separate problems. We're going to do our integral problem over to the side if we need to, and then we're going to do our limit problem. However, this one is just a straight up rule. What is the antiderivative of 1 over x squared plus 1? Yeah, tangent inverse. And we're evaluating from 1 to b. Okay, we'll give it that. Yes, no, maybe. Now, remember that we do kind of have to think backwards here, right? Because tangent inverse is the inverse. So what I'm plugging into here are not technically my x values, they're my y values. So we're saying as my y goes towards infinity, okay, so shooting up, for tangent inverse, what's my x going towards? Or in other words, where does tangent inverse have a vertical asymptote that shoots up towards infinity? Do you remember what our tangent inverse graph looks like? We should. Looks like that. Or let's also think about tangent is what over what?
Sine over cosine.
So it's going to have vertical asymptotes when
Cosine is 0.
and when is cosine 0? Or when's the first place that it's 0 on our unit circle?
Pi over 2.
Yeah, so this is pi over 2. This is negative pi over 2. So as my y values are shooting up, okay, what's my x value going to be getting closer and closer and closer to? Pi over 2. Now, do we know what tangent inverse of 1 is? From our unit circle? If we don't, it's okay. It's pi over 4, because that's where sine and cosine are the same thing. But would we all agree that tangent inverse of 1, whatever it is going to be just a constant? It's just going to be some number or angle. Agreed? So if I have pi over 2 minus some number, okay, am I still going to end up with a value, like an actual number there? Yes. So we can say that this limit converges. Agreed? We don't care what it converges to, okay? We just care that it converges. Are we all right with that? So this converges, then we must also say, or we can also say, that our sum converges. What questions do we have on that one? So we are building off of some of our previous skills of like our improper integrals. So we do have to remember how to do that in order to be able to apply our integral test. Right, so looking at our next one, could, again, does that look like a geometric series? No, okay. Again, we haven't covered it yet, but it is also not a P series or a harmonic series, so we're not going to use one of those. If I looked at the limit as n goes to infinity, notice that I would apply L'Hopital's to that, and I would get 1 over 2n, which is going to be 0, so we also can't use our nth term test. Okay. We also need to think about, though, which we didn't quite, our instructions here say that we're applying the integral test, but let's also make sure that we can apply the integral test, okay? Is that function going to be continuous? Yeah? So the only place that would cause us issues is if our denominator was 0, well then this, my first value, would need to be -1 in order for it to equal 0. Can n squared ever be -1? No. So it's not discontinuous anywhere. Is that going to be positive for anything that I plug in? Again, from 1 to infinity. Yeah, because we're squaring it and then we're adding it, right? Which both of those are already positive, so it's just getting more positive. So yeah, it's positive. And then we can kind of think about, right, my n squared is going to be increasing or getting bigger faster than just what my n would be. Yes? So my denominator is going to be getting larger quicker. So are we going to be decreasing? Yeah. So if my denominator is bigger, that means the whole thing is getting smaller. Are we all okay with that? Alright, so again, we're checking off to make sure that our integral test really does apply here. The directions tell us to use it, so it should, but just making sure that we can. So we said again, we're looking at the integral from 1 to infinity. I'm just changing these to x's now instead. Yes, no, maybe. We have an improper interval. Now this one is one where it might be helpful because there are going to be a couple of steps to go ahead and come over and just look at our integral first. What would I have to do in order to take that integral? What am I making my u? So du is going to be 2x dx. Do we have an x in there? Yeah. Do we have a 2 in there? No. So what are we going to have to throw into the front? 1/2. And then I would have 1 over u. What is the antiderivative of 1 over u? Oh. Cool. Yes, mommy. Again, this is side work, so like I don't have to be like super specific about my notation here. So I'm plugging my u back in, which was our x squared plus 1, and we are evaluating from 1 to b. I dropped my absolute values. Why did I do that? Yeah, because I have an x squared, and then I'm adding 1, so they can't ever be negative. So you can leave them there. It's just going to be redundant. It's not going to hurt it to drop them. So we have 1/2. We can go ahead and leave that factored out for right now. I have the natural log of b squared plus 1 minus the natural log of 2. Are we all okay with our integral part? Got my u sub and then how I found that stuff. Because now we need to take the limit of that thing. I have a 1/2 there. Are we okay if I pull my 1/2 to the front of my limit? Yeah, it's a constant, so I'm allowed to factor it out. So then I should have the natural log of b squared plus 1 minus the natural log of 2. Now, the natural log of 2 is just going to be what? It's going to be some constant, some not nice number, but it's still just a constant, so I don't really have to worry about that. However, what does b squared plus 1 approach as b goes towards infinity? Infinity. Are we all okay with that? So for my natural log graph, do we remember what that one looks like? increasing very fast, but is it increasing? Which means that as my x values are getting larger, what's happening to our y values? They are also getting larger, which means that this first limit will equal what? Infinity. Okay. So if one of those parts equals infinity, what's the whole thing going to do? Diverge. So this diverges. Therefore, my sum from n equals 1 to infinity of n divided by n squared plus 1 is also divergent. What questions do we have there? Alright, so the next up we're looking at our P series. Oh no, sorry, I added in too much. Let's look at this one first. This is confirm whether the integral test can be applied. Is that the last one we used? I think I just put the graph on that one. Yeah. Sorry, I just separated that. But if you're wondering, that's what the graph of that looks like, which is why we're allowed to use our integral test, because we are, notice that it is positive for the entire thing, and we are decreasing. So that's what that one was about. Alright, next up, for real this time, P series. Your P series is probably your most common sequence that you'll see. So like if you're going to only remember one of them, this is a good one to remember. Hopefully we can remember more of them, but this is a good one to remember. And we can kind of think about it, which is why it's in the same little box as your geometric, is because it's similar to our geometric. The only difference is with our geometric, your variable is in the exponent, okay, versus here, our variable is going to be in the base. But it has some similar, like, consequences then, because we're looking at something to a power. So basically, it's like when we have something of 1 divided by n to the p power, it's called a P series. So P is going to be a constant. So again, our n is our variable, and it's in my base this time. Specifically, when P is 1, so I just have 1 over n, this is called our harmonic series. And the reason we like P series is because we don't have to do a whole lot of calculus-y work with it. I don't have to take a limit, I don't have to take an integral, I just have to decide is it bigger or smaller than 1, kind of like we did with our geometric. But we can also kind of think through this just like logically, right? If I have a base, okay, and this P value is going to be getting bigger, sorry, the P value is just staying the same, but my base is getting bigger and bigger and bigger, then what's happening to that whole fraction? If I have a denominator that's getting bigger and bigger and bigger, what's happening to the whole fraction? It's getting smaller and smaller and smaller, okay? So if our P is bigger than 1, okay, we can say that this converges. Now, unlike our geometric, we do not have a nice formula that tells us what it converges to. We would have to do some more work in order to decide what it converges to, but we can say that it converges. If my P is in between 0 and 1, okay, so that means that I have a fraction there, or a decimal, right? Are we okay with that? Yeah. Okay. It is going to diverge, because we would end up having some sort of radical there, which is going to no longer make the whole fraction converge to a specific number. And if p equals 1, this is again specifically our harmonic series. This also diverges. Now, if we're talking about divergence, you do not necessarily have to say because it's the harmonic series, you can just still say this is divergent by the p-series test. So you don't necessarily have to say by the harmonic series, but it's not wrong if you go ahead. Just don't say it's a harmonic series when it's not. That would be wrong. Yes, no, maybe so. So let's look at some examples. So first, again, we just have to get used to looking at and deciding if something fits a certain form. So on this first one, okay, I have k to the negative 0.8. Okay. So it's not quite in our format. However, could I rewrite that? Yeah, how can I rewrite that? Okay, so now does that look like our p-series? Is my base my variable this time? Yeah. Is that going to converge or diverge?
Diverge.
It'll diverge because our p is less than 1. Now, it doesn't ask us for that this time, but in that case, what about our second one? Can I rewrite that?
One over 2 at the end.
Okay. So I get a fraction, that's good. Is that a p-series? No, it's not a p-series this time, because where is our variable? In the exponent this time. Okay, what could that technically be then?
Geometric.
How would I rewrite it in order for it to look like a geometric? No, I need something to the nth power.
1/2 quantity.
Yeah. Right, 1 to any power is always 1, so I can go ahead and still take that out.
Does it have to be a positive exponent for it to be geometric?
Yes. Because it has to be r to the either the n or the n minus 1, depending on where your bottom bound is, if it's 0 or 1, but it does have to be positive. Which, because we can always write that as a fraction, if it is negative, you can, I'm not going to say always, because there might be like a weird caveat to that, but usually you can do what we did there. You know, your r would just be a fraction instead. Does that make sense? Yeah, so that one would be a geometric. What do we think on C? We could rewrite it. So I'm going to have 1 over k to the 4th. Is that going to be a p-series?
Yep.
Will that one be convergent? Yep. What about our next one? I have a base, right? That's my variable. So that part's okay. But do I have a fraction? Nope. So my answer no. Alright, what about our last one? It would it converge or diverge?
Diverge.
Diverge. Yes, no, maybe, so. Okay. Question, a little bit more practice. Some of these take a little bit more working around. So it says determine whether the following series converges or diverges. So can I rewrite that first one, my a sub n on the inside, as n to a power?
To the 3 halves.
Where do we get 3 halves?
Cause any, so 1 times n to the half would be, n times the 3 halves.
Agreed. Because I have n to the 1 half plus, I would add my 1 for my other exponent. Are we okay with that? So is that a p series? Yes. Okay. P is 3 halves. So it's a fraction. Does that mean it diverges? Do all fractions diverge? No, because 3 halves is also greater than 1. So it's going to. Yep. So therefore. Yes, no, maybe? What we think about the second one? What's our p-value here? 1/3. So what is that gonna do? Diverge. What about our next one? Is it a p-series? Yep, what's our p-value? 1. So what's it gonna do? It is important to write incomplete sentences for these. Alright, what about our last one? Is that one a p-series? Okay, well my directions don't necessarily say I have to use a p-series test, right? They just say that I have to figure out if it converges or diverges. Agreed? Okay. So can I rewrite that?
Yeah.
Yeah. What can I rewrite that to? 1 over
E to the n.
e to the n. Okay. Could I rewrite that? So, is it a p-series? Where does my variable have to be in order for it to be a p-series?
Base.
In the base. Is my n in the base this time?
No.
No. Okay. So what's our other one where the n or the variable is not in the base?
Geometric.
Geometric. Can I rewrite that as a geometric?
Yeah.
Yeah. This is again kind of like I did with the last one. This would become 1 over e to the nth power. Yes? So then we have to think, when does our geometric converge?
R is between 0 and 1.
Is r between 0 and 1? Yeah, e is a constant, but what is e approximately?
2.7.
2 point stuff, right? So if I have 1 divided by 2 point stuff, okay, is that still going to be between 0 and 1?
Yeah.
So we could say therefore converges because geometric series. Now it doesn't ask for it, but how would I find my sum then if it's a geometric? What's our formula? Yeah, our a sub 1 divided by 1 minus r. So if it said like, and find what it converges to, then we would take it a step further. But it doesn't, so we can just say therefore converges because it's a geometric series. Questions on those?